Look up at the night sky. Every star you see is a furnace of creation, burning, shining, shaping the universe as we know it. Now imagine, all of them gone. No light, no warmth, no motion, just eternal darkness. That's not science fiction. It's the universe's final fate, a state physicists call the heat death. It's not an explosion or a collapse. It's something far colder, the slow fade into absolute stillness, where even time itself loses meaning. But how does a living, expanding universe end up frozen in silence? To understand the end, we first need to understand how it all began. 13.8 billion years ago, everything, every particle, every photon, every force, was packed into something smaller than an atom. Then, in an instant, it expanded outward, the Big Bang. Space itself began stretching. Temperatures soared above 10 to the 32nd Kelvin, so hot that matter and energy were indistinguishable. As the universe cooled, particles began to form. Protons, electrons, atoms. Then gravity took over, sculpting the first stars and galaxies. Those stars forged the elements that built planets, and eventually us. But there's a hidden cost to all of this creation. Every time a star burns, every time energy flows, the universe loses a little bit of its usable energy. That loss is measured by something fundamental: entropy. Entropy is often called disorder, but that's not quite right. It's a measure of how evenly energy is spread out. When something happens, a star burns, an atom decays, a cup of coffee cools, energy flows from concentrated to diffuse, from order to balance. Over time, this trend is inescapable. The second law of thermodynamics says entropy in a closed system always increases. The universe itself is the ultimate closed system. Every second it grows more even, more balanced, and a little bit closer to its final state, thermal equilibrium, when everything everywhere reaches the same temperature and nothing more can happen. This is the seed of the universe's death. Not fire, not violence, but the quiet march of entropy. Fast forward trillions of years. Galaxies drift apart as space continues to expand. Star formation slows, then stops. The great stellar factories, nebulae, have run out of the hydrogen gas needed to ignite new suns. The sky begins to dim. The last stars to shine are small, faint red dwarfs. They burn slowly, living for trillions of years, far longer than our sun ever will. But eventually, even they exhaust their fuel. They'll collapse into white dwarfs, cooling cinders of once living stars. Over time, eons upon eons, those white dwarfs will cool to the temperature of the universe itself, fading into invisible black dwarfs, stars that no longer shine. The age of light ends. The stellar era is over. But in the darkness that follows, one last force remains: gravity. With no stars left to resist, gravity becomes king. Black holes dominate what remains of the cosmos. Vast, hungry wells devouring the last bits of matter. Entire galaxies are consumed by their central black holes. Smaller black holes merge, creating titans billions of times the mass of our sun. But even these cosmic giants are not eternal. In 1974, Stephen Hawking discovered that black holes aren't perfectly black. They leak energy, faint radiation caused by quantum effects at the event horizon. This process, called Hawking radiation, means that black holes slowly evaporate over unimaginable timescales. A small black hole might disappear in 10 to the 67th years. A supermassive one, like the monster in the center of the Milky Way, could take 10 to the 99th years to fade. One by one they vanish. When the final black hole evaporates, it will release its last whisper of warmth into the void. After that, there is nothing left that can do work, move, or change. The universe enters its final act. Now begins the dark era. No stars, no galaxies, just scattered particles drifting through an ever-expanding void. Temperatures drop to fractions of a degree above absolute zero. Even the faint afterglow of the Big Bang, the cosmic microwave background, has faded into darkness. Matter itself starts to decay. Protons, the building blocks of atoms, may eventually break apart after 10 to the 40th years, leaving behind nothing but light particles spreading thinner and thinner. At this stage, the universe is a featureless expanse, cold, thin, and utterly still. Entropy is nearly perfect. Every gradient, every imbalance is gone. In this era, time becomes meaningless, because time only moves forward when something changes, and when nothing changes, time, in a sense, stops. This is the heat death, the end of all physical processes, the final frozen balance of everything that ever was. But is that truly the end? Some physicists don't think so. Quantum theory tells us that even in total emptiness, the vacuum itself isn't stable. Tiny fluctuations constantly appear, particles popping in and out of existence. Over inconceivably long timescales, one of those fluctuations might grow large enough to trigger a new Big Bang, a fresh burst of energy, a new space-time, a new universe. If that's true, the death of our universe is just one heartbeat in an infinite cosmic cycle, a never-ending rhythm of birth, expansion, death, and rebirth. But if it's not, if this really is the end, then the story of existence ends not in fire or collapse, but in peace. A quiet universe, stretched thin and cold, where everything that could ever happen already has. It's a haunting thought, but also a strangely comforting one, because even as the last photon fades into darkness, the memory of everything, stars, galaxies, life, is written into the fabric of space itself. If you enjoy this type of content, subscribe and comment below which part of the video you found the most fascinating.